We continue to cover details of evolutionary algorithms by considering selection of individuals for the next generation and also crossover and mutation operations applied on chromosomes in order to change them. For the selection of the individuals for next generation, we are going to consider tournament selection. Other selection algorithms, for example, roulette wheel selection, may be used for this purpose also. In the tournament selection, we have a tournament size. We consider tournament size arbitrarily chosen individuals from the population. In the algorithm, the best of these individuals means tournament and will be chosen. The higher the fitness, the better chance to get chosen. Here is the summary of the tournament selection algorithm. Then we will see the details of the algorithm. It is saying that choose initial best randomly and repeat this part team size, tournament size times and return the best. In the loop, choose an individual randomly, match between individual and best, whichever wins is the new best. In fact, match between individual and best is comparing the fitness of the new individual and the best one, whichever is higher is chosen. This is repeated tournament size times and the algorithm returns the best among that number of individuals. The code for the tournament selection is given here. The return value is a pointer to an individual. In fact, the best one will be returned. The parameters are a pointer to population named pop and an integer showing the tournament size. The name of the function is tournament selection, pop tournament selection. We have individual pointers, int and best. These are the competing and best individual. Initially, we are setting the best one as the individual at position, which is randomly chosen by choosing a random number and then multiplying it by the population size and cast it to integer. So this is a value between 0 and population size, and randomly one of the individual is chosen as the best one. But later it will be updated. Choose initially best randomly. While we are decrementing the team size and comparing with 0, while team size is greater than 0, we are randomly selecting team size number of individuals. We are setting individual as the member in the individuals array at the location determined by a random value multiplied by the population size casted to integer. So randomly an individual is chosen from the population, and then the fitness of the individual is compared with the fitness of the best. If this is the case, if the fitness of the new individual is better than the best, then best is set as the individual. If it is better, then it is the new best. This is the end of the loop. This is repeated team size times. So among that number of individuals, the best is chosen, and that one is returned. Return this individual. This is the end of the tournament selection algorithm for one tournament. Now we are considering the selection of individuals for the next generation, in which we are using the tournament selection that we considered just now. Maybe elitist approach may be used. In that case, the best one will be transmitted to the next generation without any change. The name of the function is population select. We have arguments population, tournament size, and elitist. We have loop variable, integer I. We have an array of individuals called P. Each entry is containing a pointer to an individual. This is the exchange buffer. I is set to population size. If elitist approach, int individual copy population buffer at location I, which is decremented by 1, and after that, into that location, population best is copied. While we are each time decremented I by 1, and we are comparing if it is still greater or equal to 0. If it is the case, we continue in the loop. We apply individual copy from the population. We are selecting tournament size individuals, and we are applying population tournament selection function. So this one returns the best of the tournament, and that best among team size, tournament size individuals is stored into the location population buffer I. And then we have a swap operation. We are setting P as the population individuals and population individuals as population buffer and population buffer as P. So after these lines, we have a swap between population individuals and population buffer. It's shown here. So we are setting the selected individuals in the population. Population best is set as null. Best individual is not known yet, but later by applying the related algorithm that we considered previously, the best one in the population will be determined by evaluating the individuals in the population. Two important operations that change the content of chromosomes are crossover and mutation. Crossover is exchange of a piece of the chromosomes between two individuals. Here, we are going to consider a crossover which is called one-point crossover. For this purpose, choose cutting line between two genes by random and then change sequences of genes on one side of the cutting line. An example is shown where cutting line is chosen as 2. These are the original parental chromosomes. Notice the content is as given here. This is shown, one of the parent is shown by white and the other one with gray. And the fitness is -2 for the first chromosome, and it is -3 for the second parental chromosome. By the crossover, the part at the other side of the cutting line is exchanged. So these values are copied to this chromosome, and these are to that one. So after crossover, the chromosomes that we obtain are as given here. This is the original content, and this part is the content coming from the other parental chromosome. And similar for the other chromosome. Here, this is the original content, and this part is copied from the other chromosome. And notice that the fitness of the new chromosome created in this way is 0 for this one, and it is -3 for the other chromosome. Now we are considering the code for the crossover operation. This is individual crossover operation. We have two individuals as parameters, individual 1 and individual 2, and these are pointers to the type individual. There is no return type, it is void here. We have loop variable I and an integer k, this is gene index of crossover point, and another integer t for the exchange of the value of the genes. First, we are trying to find a crossover point randomly. K is set as a random value multiplied by the value in the individual one for the number of genes -1. So this is generating a value between 0 and n-2. And then we are incrementing it by 1. So we have a value between 1 and n-1. Here, notice that whatever created here is casted to integer. So in this way, we are choosing a crossover point randomly. And we are checking if k is greater than the number of genes divided by 2. That means that if this is larger, we have to copy the second part because it has less number of elements. Otherwise, we will copy the first part of the genes, first part of the chromosome. If this is the case, if k is larger than the half of the number of genes in the chromosome, in that case, we are setting I to individual 1n, this is the number of genes. In the other case, we are setting I to k, and we are also updating k to 0. And then each time we are decrementing I by 1 and compare with k. We are traversing the smaller section. I and k are adjusted here. And this is a swap operation. Into T, we are storing the value of the genes I of individual 1. Then we are setting individual 1 genes I with the individual 2 genes I. We are loading the ith gene to the first one from the second one. And then we are setting the value of individual 2 genes I to T. So this is swapping the ith gene between individual 1 and individual 2. And then the value of the fitness for individual 1 and individual 2 are set to 1. So we invalidate the fitness of the changed individuals. They will be calculated by the evaluate operation later. This is the end of the individual crossover. And we have to apply this crossover to a certain rate of individuals in the population. Certain rate of individuals is submitted by crossover. Include of both crossover products in new population. Parental individuals are lost here in this code. No crossover on best individual is applied if elitist approach is used. We are going to apply crossover on consecutive individuals in the population, in the array individuals, and this is applied up to a fraction of the population. This is the code for the population crossover. We have a population pointer as the argument and also a double value showing the fraction. We have two variables, I and k. We are setting k, population size -1 multiplied by fraction. So we are determining what is the point up to which we are applying crossover. We are determining that one. And for I, we are setting to 0, while it is less than k we are doing. Each time we are incremented by 2. So we will take pairs of individuals in the array. Crossover of pairs of individuals. We are calling the function individual cross that we considered just previously. This is calling it with the individual of the population at I position and I plus 1 position. We are sending these consecutive individuals, for example, these two, to the individual crossover, and those individuals will be updated by the crossover operation. The other operation that changes the content of the chromosome is mutation. Mutation is replacement of randomly chosen genes. So it is changing of alleles. Perhaps number of replaced genes is chosen by random. Notice that the number of replaced genes should be as small as possible. Consider this chromosome and suppose that in the operation these genes are chosen to be updated, and after the update operation the content of this one may become 2, for example. It was 4 previously, and the content, the value of this gene may become 4, which was 3 previously. And the other genes remaining the same. The fitness is -2 for the original chromosome, and it becomes -4 after the mutation operation. Notice that mutations are mostly damaging, decrease the fitness, but non-existent alleles can be created by mutation only. Here is the code for the mutation of the individual chromosome. We are deciding whether to continue mutating or not randomly. The best individual, if taken over, won't be submitted to a mutation. The code for mutation of individual, we have a parameter which is a pointer to an individual, and also another parameter which is the probability. This is the mutation rate, and there is no return value. We are choosing a random value and comparing with probability. If it is greater than probability, then we are returning from the code. We are determining whether to change the individual or not. If this is the case, without mutation, it returns. Here there is a loop. which is updating the gene in the chromosome, which is randomly chosen. The index is decided such that a random value is chosen, multiplied by the number of genes in the chromosome, casted to integer. So we have a value between 0 and I-1. So that gene in the chromosome is updated as, again, the value is decided randomly. It is set to a value which is a random value multiplied by n casted to integer. So it is set to a value which is between 0 and n-1. And remember that this is showing the location of the queen as column. This is column number for the gene decided by this index. And this is repeated while the random value is less than probability. Each time we are choosing a random value in the loop and we are comparing with probability. So we are deciding to continue randomly. So as a summary, randomly change random genes. Fitness is no longer known after the mutation operation. Because of that, the fitness of the individual, which is the parameter here, is set to 1. This is the end of the individual mutation. This is the code for the population mutation. The parameters are a pointer to population type variable, pop, and we have a probability. We have an integer, this is the loop variable. We have for loop. Initially, the value of the loop variable is set to population size -1. Each time it is decremented by 1 and compared to 0. And inside the loop, we are calling the individual mutate. We are calling it with population individual I and with the probability decided here as the parameter. So mutate sum of individuals in the loop. This is the end of the population mutate and also the end of this part of the lecture.